Okay, so we're going to do an example now, calculation with the and we'll use this troll field. We've got the reservoir temperature we found was 71 degrees C, I think, from the one reference we found in the beginning. The initial reservoir pressure we found was about 158 bar. Isn't that correct? I think what we had found, something like that. And the question then is the gas composition. YI. Now, we haven't, I don't know if we went through these definitions yet, I don't think so. But basically, molar composition is defined as the moles of component I, in this particular case, in a gas phase, divided by the number of moles of total gas. Okay? So that's a mole fraction. That's how it's defined. Now, another thing that Standing and Katz did is that the situation where you don't always have the gas composition, they provided a means to estimate this is also from Standing and Katz, to estimate the pseudocritical or average critical temperature and pseudocritical pressure, knowing only the gas molecular weight. More precisely, the gas specific gravity, or in SI it's called relative density. Okay. Okay. The gas relative density is defined as the gas density at standard conditions divided by the air density at standard conditions. And we're going to use our 60 degrees Fahrenheit and 1 atmosphere. And what you can show is that if you assume the Z factor is 1 at these conditions, at standard conditions, that basically is the same, because density only becomes a function of molecular weight, that this is the same as the molecular weight of the gas divided by molecular weight of air. Okay? That's because gas density, which is the mass of gas divided by volume of gas, right? That's the same as the moles of gas, right, times the molecular weight of gas. We agree? Mass is equal to moles times molecular weight. And from the gas law, this Ng over volume G is just equal to the pressure over RTZ. Is that right? That's from our gas law. Well, this term here at standard conditions is the same for any gas, for example, air. So that's why it cancels. Okay, that's the same for any gas or air. So that term at standard conditions will cancel, and we're left only with the ratio of molecular weight. And this is often measured, available, while composition may not be. At least in the old days, in the 1940s, when they were doing this work, 50s and 60s. There are ways to measure this specific gravity. It was much more accessible to get that number than it was to have the gas composition. So to help the engineers who didn't have composition, but they did have some estimate of the gas-specific gravity. By the way, this is the gas-specific gravity of the reservoir gas. Okay. They came up with a correlation standing in cats for TPC as a function of gas-specific gravity and average critical pressure as a function of gas-specific gravity. I'll fetch that into the okay. Okay, that's this chart here. It's kind of hard to read, so I'll just I think we can just bring it in there. Okay. And the correlation is not completely unique. You can see they have a correlation for California gases, for Oklahoma City gases, what's called condensate fluids. And the condensate fluids are these fluids that contain a lot of this C7 plus stuff, as much as 10, maybe 15 mole percent C7 plus. So they're not completely general, but if you have an estimate of the gas gravity, you can go in and read off this chart an estimate of, in this case here, it's the these go here to the left. So these basically, this is our pseudocritical temperature plot and our pseudocritical pressure plot. Okay. And the troll gas is a very lean gas. It's 90-something% methane. That I can tell you. Now, whether we can find that on the internet or not, I don't know. We'll take my success on Googling is not particularly good right now, but let's just try troll field gas gravity. See if we can find.
Have you done a lot of work with troll?
Yes.
Okay.
This doesn't look too promising. Let's see, gas specific gravity. This is the oil. We have to do this unique because it also has oil beneath it. Okay. I don't think we're going to find it right away. So let's just go with Curtis's best guess that for Troll, gas specific gravity is approximately 0.6. Okay? It's that lean. Okay? So we go in, this is 0.6 here. So we go in and there's an equation for this as well, but in the book we'll just read that value there. 360 degrees Rankine. For TPC. And then we've got about 670 psi for the pseudocritical pressure. Okay. So TPC 360 Rankine. What is that in Kelvin? How much? 200. Exactly. That's not bad. Yeah, I guess 1.8. There we go. And this conversion is 14.5. That's good enough for, what we're doing here. PSI per bar. So how many bars is this? $46.2. 6.2. Okay. Yes?
Did you take two different X values, or is it meant to be the same X value for both, or not?
Oh no, I did. I screwed up. Luckily, this is fairly flat. This is
Probably not much difference anyway.
probably not that much different, but yeah, you caught that. It went off the scale, so it's this first line here, which makes the 670 even closer. Sometimes you got good days, sometimes not. The minor ticks on this is 5 degrees or 5 psi. So, okay. So the pseudo-reduced temperature would be the reservoir temperature, which was what, 273. And so we have that on the Excel sheet somewhere here. Be this one here, 344.15, 273 plus the 71, and that was 344 Kelvin over the 200 Kelvin. And that should be 1.7 something maybe? 1.72. Okay. And this is at initial pressure. I think I said it was pressure was 158 bar. Divided by the 46.2 bar. It's 4 something. Maybe 3 something.
3.42.
Okay. Yeah. And since we're going to do this graphically, we only need the 1.7 and the 3.4 because our eyes just aren't good enough. 1.7 and 3.4. That's kind of easy to remember because it's twice. And we can go up here, and I'm just going to fetch this, bring it down to the bottom, and I'm going to blow it up a little bit. So we can read it. Okay. It was 3.4 in pressure and 1.7. So 1.7 is this line here. And 3.4 would be right there. So pretty close to right there. And then we've got to bring that across to the left. It'd be right there. And that's pretty close to 0.85. So it's 15% deviating from ideal gas behavior. 15%, which is a lot for engineering. So you got 1.7 is the reduced temperature, 3.4 is the reduced pressure, so the Z factor of the gas initially in control about 0.85. Okay. I know this is old school with using charts and calculators and correlations. Any questions? That's 0.85. Now there is an Excel sheet that is in the what's called the E-notes under gas PVT, and this Excel sheet is called EX-1, example 1. Should be changed, but it's an Excel sheet for calculating gas PVT properties. Okay, and it's got Visual Basic for solving that complicated equation describing the standing gas chart. Okay, so we'll take a look at that and see if we get something similar. You have to enable the macros here, and I think if you want to get this set of E-notes, then what you have to do is go on to the website. Under courses, PVT flow, and there it is there. It's a single zip file. Okay, it's a single zip file under the same directory as where you've been fetching things now is 2012 TPG 4145. Ooh, that's not what I want to do. but you want to go up a level to the E notes, and then you can download that. All right? And then when we do that, we'll get this thing here. And what you see is that gas properties, and you have to input what's in red is required to input. So temperature in degrees C, that was what, 71? The gas specific gravity we estimate, 0.6. You can see that in pink, if you actually have the composition and the properties of the C7 plus, it'll calculate it with this more accurate mixing rule formula. Okay? And somewhere or another we'll come up with the troll gas composition at some point and check this. But right now what it's going to do is that it's going to, since it's got this 0.6, it's going to use that with these correlations by Sutton, which are best fit to the charts that we were looking at. These charts here, there's a fellow professor at the Colorado School of Mines, some of you may go there next year, who fit kind of best fit equations for these two. And they're by this guy named Sutton. So that's what we get here. And he's getting 196 Kelvin. We got 200, right? That's not too far off. It's about, what's that, about 2% different? Right? It's 4 degrees Kelvin divided by 200. It's about 2% different. And he gets a 46.7, and we got 46.2, which is a little more, 1% difference. Not too bad. So they're pretty much the same numbers. But that's just to get the pseudocritical pressure and temperature. This next sheet, gas PVT, as a function of pressure, that's where it calculates the pseudo reduced pressures, and then it uses this complicated equation in the book, chapter 3. I'll show you that. It's this equation here. You see this equation here? Z is equal to alpha times reduced pressure divided by y, and then you have to find y by solving this very nonlinear equation. You have to find y that drives this thing to 0. So it's like you have to solve by trial and error. And then to do that, you use the Newton-Raphson method because it's trial and error. So give you the derivative to help in that Newton-Raphson, and then once you find it, you have the y value, then you have the z value. So this little there's a routine called z-fac, and to see that in Excel, you have to go to the Visual Basic mode, and I think that's Alt F11. Okay. And you'll see some of these, terms that are in the book. You've got this 0.06125, 0.06125, etc. You've got the function, you've got the derivative of the function, and then you've got this. It's kind of like it'll go time and time again until it finds something. Yeah, it says it'll give you 100 tries. And it's trying to drive this function to 0 or something close to 0. So if you're interested in programming and things, then this is that derivative that's given here. So anyway, that's what's there. Okay, and it gives us this. Now we want to see what it gets for the z factor at what pressure? 46.2. This is 46.2. Doesn't have that. We have to put it down here. 46.2. That's not good. 46.2. It's getting 0.95, which is not what we want to see. Okay. .7. Well, let's see here. It's got 1.7. That's pretty close. And this, okay. See, this one's not calculating right. This column here is pseudo pressure, pseudo reduced pressure, and that should be not 0.99. That should be something like we got 3.4. So I must have screwed up when I, let's see here. See, it's A39 divided by B9. Well, B9 is that. Oh, okay. I messed up here, guys. Is 158 we want to calculate it at. Right? It's 158 is the pressure we want to calculate it at. So we're going to go up here, 158 there. Now that's a little better. Then we get a reduced pressure of 3.4, and we get a 0.88. So it's getting 0.88, and we got 0.85. Well, it's not great, but it's... This should have been left at 50. Okay. So 3.4 is the reduced pressure, and then this equation solves 0.88. A little bit surprised it was that far off. I might have misread it. Let's see here. 3.4. It was actually 1.72, right? So it would actually, this is 1.7, this is 1.8, so it should have been a little bit higher here, something like that. And that line, it's more like 8.7. 0.87 should have been what we read it off. If we would have read it properly. That's getting pretty close. About 1% different. Okay. All right. Any questions then about how this works? Okay.
Sorry, just the specific gas. Is that relative to air? Obviously. Maybe.
The specific gas is
It's relative to air, is it?
to air, yeah. Yeah. Yeah, that was this. This is a definition here.
Okay.
You also have a specific gravity or relative density for liquids, and it's relative to water at the same standard pressure and temperature. But of course, you'd be dividing by density, 1,000 kilograms per cubic meter, instead of the air. And often we would write, and in the book it's always written this way, there's no units, but we actually write it this way. Okay? So that it's clear. If somebody's sloppy, they forget the G on the specific gravity. I think that trying to think. I think that's pretty much it. What I will show you is the Appendix B, basically has a worked example. The first couple of worked examples in the Appendix B are for calculating gas properties like Z factor. So you can see how it's being done there. It's for a simple gas composition like this. This is actually not a reservoir gas, obviously. Okay, so that's Appendix B, if you have any questions. Otherwise, I don't have a lot, unless you have questions about this. Then we can call it a day, an evening. All right.